All right, thanks everyone for coming. Today we have Sophia Brumer with us. She's visiting from France. Sophia got her bachelor's from University of Southampton in 2007. Is that right?
No. I'll explain it.
All right, she'll explain. But Sophia spent 15 months at UM as an exchange student, and that's how I met her. For a year, we shared an office actually, so we're good friends too. Then at 2017, she got a PhD from Columbia University in ocean science, oceanography.
It's called Earth and Environmental Sciences.
Earth and Environmental Sciences.
Yes, interaction.
And then after that, she moved to France, where she worked at LAERO, which is one French national lab, and now she works at LAERO, which is another French national lab, and she can tell us more about it. And her talk today is on sub-mesoscale Earth interactions in extratropical cyclones. All right, take it away, Sophia.
Well, thank you for having me. I figured since I'm visiting family, it's a good opportunity to also stop by on the old stomping grounds and where it all kind of started. So I'd like to take this opportunity to give you an overview of the research I am doing since for the last year and a half that I joined the Laboratoire d'Aérologie in Toulouse. It's a meteorology lab. It's actually the lab where they developed the French research weather model. And this is work I'm doing with my last postdoc advisor, Florian Pontillon, and what we call a research engineer, Jean-Louis Canez, who's in charge of the coupled modeling framework in France. All right, so to get the story straight, I did what they call an integrated master's at the University of Southampton. So it's a master's in 4 years. And in my third year of that master's, I had the opportunity to be an exchange student here at UM and at Erasmus. I was kind of the guinea pig on that exchange program. And so I had carte blanche as to what classes to pick and what to do. And so this is really where my research in Earth interaction started, in the lab of Shui Shen, and where I took all sorts of interesting classes that convinced me that, yes, I didn't just want to study physical oceanography to live by the ocean, but also because it's pretty cool and interesting. I ended a PhD at Columbia University with Chris Zappa, where I worked mostly on observations. And I guess my greatest contribution stemmed from the opportunity to participate in the High Winds cruise. It was a cruise dedicated to measuring fluxes of momentum and heat, but also of gases, particularly sparingly soluble gases such as CO2 and DMS, during storm conditions. So as you can see, this was a picture from the cruise. We managed to convince the crew to head into storms, wait for the storms head on, and get hit by wave spray and whatnot. And we got the first measurements for those gases around 25 meters a second. And so what I'm showing you here is kind of the key results from my thesis. It's a gas transfer velocity, which is usually parameterized as a function of the 10-meter mean. This is for CO2. And the dots are different cruises, different data sets, and you can see that at high winds you can start to see divergence. And a simple wind dependence is no longer good. And that's because at winds over 10 meters a second, you're going to have wave breaking, waves and bubbles. They're going to promote gas transfer. So what I did, this is just one of the examples, is try other parameterization here to form a Reynolds number that includes some information about the sea state. And it nicely shows that if you input here, it's just the significant wave height, you get all the different data sets and show similar trends with this Reynolds number. So that was my PhD. That was largely based on observation, a ton of different projects, but that was the main one. And after graduating, I decided to go back to Europe and join the Laboratoire d'Océanographie Physique et Spatiale in Brest on a project around air-sea wave coupling in the coastal zone. And from then on, I kind of continued on working on the couple modeling for different applications, and of what had started here at Erasmus with different models. Okay, and yes, last but not least, so in 2023, I moved to Toulouse on a postdoc, and then was hired as a CNRS, so that's a national government researcher. Just recently, I started in October, and for that, I had to write a project of where I wanted to go, where my research was going to be. So my ambition is to gain a better understanding and to quantify the role of sea state and obviously wave breaking. So these are topics I've done since my grad school, and sea spray on wind and rain extremes of low pressure system. Now I included low pressure system of any kind. In Europe, we're more interested in extratropical systems, but I also have a grad student working on tropical cyclones. So now the issue is that we're looking at a problem that ranges a wide scale, like spatial and temporal scales, from micrometers, from nanometers for aerosol, micrometers for sea spray, to thousands of kilometers for a extratropical depression, and things that happen like in some milliseconds to several days. An issue as those like small scales and high winds, we have very uncertain air-sea fluxes, and we have barely any idea of how much sea spray is produced, and if we think that sea spray is important once we have wave breaking, this is one of the big unknowns. In terms of fluxes, there's a lot of inconsistency in the way we model them, in the sense that we use parameterizations that have been validated for data under 25 meters a second, so rather the lower wind speed, and that in the way we couple our models, we don't take into account the whole complexity of what we have. So not only like the heterogeneity, spatial and temporal heterogeneity of the sea state, of the temperature, of whatever you want, and we're starting to couple now at under kilometer scale and having like weather, numerical weather models that are going to 500 meter resolution and so on. So we need to start asking us questions of how do we go beyond these physical inconsistencies. So I would like to continue working on coupled modeling, introduce again observations with a focus on extratropical cyclone, in order to have a coherent framework that includes the impacts of wave breaking, of sea spray, and also the fact that, so here's an example of a classical extratropical storm with a cold front and warm front, of the fact that you don't always have alignment between the winds and the waves, that you have all the seas and the seas. And all of that is not really taken into account in our coupled model frameworks. Or even we can't easily take it into account when we analyze data, because data is quite sparse and we don't have enough examples, or we should relook at old examples to kind of combine them in a way that makes more sense to try to study those things. All right, so that was my project, but what I'm going to present to you today is what we have started to do with the group at LAERO. And so I'm going to walk you through 3 case studies of extratropical storms: Storm Adrian in the Mediterranean, Storm Alex that hit the coast of Brittany. I lived up there in Brest at the time. I don't remember it. It was one of the many storms that passed by. And then a storm that resembles somewhat of a hurricane, called actually a Medicaid, in the Mediterranean. That was the case of Yanis. So the kind of goal of our group is to understand the processes, the small-scale processes that will bring down the strong winds at the surface, and how these are impacted by surface processes, be it waves, wave breaking, sea spray, and so how these small-scale processes impact the larger scale, the mesoscale processes. So this is the conceptual picture of a extratropical cyclone with a warm conveyor belt, a cool conveyor belt here, a dry intrusion that brings tropospheric air down, and this inject that is thought to bring high momentum air also from the cloud head down to the surface and to be responsible for the strong winds we have in those kind of systems. So this picture is pretty well understood. However, what happens in the lower boundary layer, how the high momentum air actually comes to the surface, is something we don't quite know. And as I said, these processes around wave breaking and sea spray are also pretty unknown. So let's start with the first case study. This was a case study actually studied by a graduate student of Florian Pontillon. When I arrived, she was finishing her PhD, and I got to be involved in her second paper. So this was a pretty strong storm in the Mediterranean. Here on the right, you see the track. Here you have Sardinia, Corsica, and kind of went from there to there. Caused a lot of fatalities with quite strong winds. And so what she did is she used the French weather model, so Meso and Ash, and she did a series of simulations starting at kilometer scale and zooming down to, actually she went down to 20 meters, but here we're going to show you the 200 meter resolution. And she then focused in this zone where you have the strongest wind. So now, obviously, at 1 kilometer scale, you are parameterizing the shallow convection, and your turbulence is also fully parameterized. However, once you start going down to 200 meters, you're in what we call large eddy simulation. You don't need to have a parameterization for shallow convection, it's explicit, and you start to resolve the largest eddies, so turbulence is partially resolved. And so what she did is she looked at where these high winds at the surface came from, and so she did back trajectories. And here you have the trajectories back in time, and here the evolution of the height of these trajectories and the wind speed. So you can see that those trajectories associated to the highest wind at the end, well, at the time where she was looking, they stayed within the last 6 hours, they stayed under 2 kilometers, so within the boundary layer. So it's associated with the cold conveyor belt. All right, and then she looked at the details of what did it actually look like. So that was a little white box that you had in the previous maps. And what you see here is a map and a cross-section of the wind. And you can see that you have coherent structures in that region. And these coherent structures are rolls. And then she looked at the momentum transport associated to those rolls and found that those rolls bring high momentum down. The downward motion is more pronounced than the upward motion, so those rolls are responsible for bringing the high momentum air really down to the surface, so would induce the wind gusts that cause a lot of damage and so that's the time I came into the lab, and then she said, okay, so we have wind rolls, and I want to know how these wind rolls, how sensitive are they to the surface flux parameterization, to surface fluxes. So in the French research model, but actually also in the French numerical prediction model and the climate models, we have a common interface, surface interface. And here are the choices of parameterizations that we have. EQM6 is the operational one that they use in France, and it's a purely parametric. These three kind of all built on the core algorithm, one that includes sea spray, one that was developed by my postdoc advisor in France that includes some, in Brest, that includes some dependence of the drag coefficient on the wave age. And so what you see here is the momentum flux plotted against wind speed for these four parameterization. You see that core and Andreas just keep increasing with wind speed, which is likely, which is false. And then EQM and WASP force the drag coefficient, well, the momentum to decrease at higher winds. So this one, EQM is purely parametric. This one is through fit with changing the wave age. And here you have the sensible and latent heat fluxes, and you can see that you have variability between the different parameterization, and you have Andreas that just boosts your heat fluxes. So these are the parameterizations that are available in that code. So she just ran some sensitivity tests, and what she found is that with the reference, which is for core, let's say you have a certain size, A size rolls at the surface bringing down momentum. If you boost the heat fluxes, those rolls are going to become bigger and bring down more momentum. They become taller but narrower. And if you remove the sensible heat, you don't have rolls at all. Okay, so that was just looking at how, yes, some surface effects impacts the high winds, but it was without coupling. So, oh yeah, right, sorry, forgot I had a slide. I was talking about rolls, and rolls is something that they look at now a lot in the satellite community, the SAR satellite community, but these are SAR images where you see roughness of the surface for different stability conditions, and they've classified them under stable and unstable conditions, and you can see that near stable condition you have those kind of streaks that resemble the rolls, and they did a kind of a global analysis of the SAR data with ERA 5 compared to ERA 5 winds and the Richardson number they calculated from the ERA 5 data, and kind of classified where you find which kind of structures depending on stability and winds. So now obviously the rolls we see are at much higher winds and different stability than what they have in in the global ERA5 data set. So we're working on them to try to see also in the SAR data, because we have some cases of a storm with SAR data, if we find similar structures in our model of those walls and to what they find there, because that's still an unknown. How to interpret the SAR roughness is still a big challenge. So one of the next cases we look at, and that was actually the case study of my last postdoc, is the storm Alex here. So it did a funny, has a very funny path, because it actually hit Brittany, which is quite classic, but it looped over the channel before it headed north. So the situation I'm looking at is when it first hit Brittany. And there, so we said, okay, they did a first study where they looked at the impact of fluxes without any coupling, and so for this one they added wave coupling. And so this is like part of the coupled model we have in France and we use. So it's a French weather model, and then wave wedge tree for the waves. And what was interesting for this study is that the French weather model was just rewritten to work on GPUs, which allows to do some pretty neat high resolution full storm scale modeling, which is what they did before I arrived. So they went down in resolution. It was on a new computer, so it was also a computational challenge to make sure it all works. So they gradually went down in resolution up to 100 meter resolution on this one domain. So as you can see, the grid size is quite substantial. And within this domain, what I did is rerun runs where I have back trajectories. And I also did a classic 1.6 kilometer NWP simulation. And the goal there was to try to look at, again, what is responsible to the strong winds at this time. There was suspicion of a sting jet, so I showed you on the conceptual image of an air mass that comes from the cloud head and brings down high momentum air to the surface. So it's trying to see how to describe it and what do we gain from going from 1.6 to 100 meter resolution. And let's see, does this work? No. Let me see if I have still the link. This is just to show you a cool animation.
Is Surfix the
Yes.
surface framework that your group developed?
So no, it's another lab, but it's the one we use.
Okay.
So we develop within Surfix. So we work on the air. So Surfix is the surface model that includes also overland, like parameterization of a lake and so on. So we develop the sea part. Yeah, absolutely. Oh, I guess it's not working. So that was just an animation of the 100 meter resolution run, because it's pretty cool, but never mind. All right, so I did on the 1.6 kilometer run, I did the back trajectories, which I showed you here. We centered around the storm center, minimum of pressure. And I distinguished three classes simply by looking at how they change, how the altitude changes. So I see that there are a class that starts high up and plunges just at the end. There's one that stays low. I put a threshold at 2.5 kilometers. I say everything that's below it's a full conveyor belt. And then I have some that go up and down, but do plunge at the end. They're hitting here in the red, and that's what's in sting jet. And if you look details, it comes from the cloud head. It fits all those patterns. So you can see that the sting jet and the cool conveyor belt is loops around the center of the depression nicely, whereas the dry intrusion comes from a separate geographic region and plunges at the end. And so these, all the trajectories responsible for winds over 35 meters a second at the time I am interested in. Okay, so knowing that, I looked also at the details of the humidity in each trajectory, the relative humidity, and I found that within the last part of the descent, the dry intrusion is under 70% and the sting jet is over 70%. So I'm going to look at the high resolution run just at the end, because I have to rerun the trajectories. It's a lot of data, a lot of computationally, it's not that easy. So I'm just going to focus on the last part, and I need to be able to distinguish the sting jet from the dry intrusion, so I'm going to put a criterion on the relative humidity. And so this is what you have here. Here are just the proportion of trajectories in each of these categories. I listed here my thresholds that I set. And you can see that the winds over 35 meters a second are largely due in the lower boundary to the cold conveyor belt. So this is based on the 200 meter resolution run. I didn't do it on the 100 meter resolution run yet because it's pretty hard computation. So here I'm showing you the number of trajectories. You can imagine the hundreds of thousands. There's the evolution, as we expect, the dry intrusion and the thing that comes at the end. The cold conveyor belt remains pretty constant. And you can start to see details that I didn't have at, I'm not showing it to you, but that I didn't have at 1.6 kilometer resolution. You can see that here's the median, that the dry intrusion actually is lower than the sting jet. However, these are the quanta, the 25th and the 75th quanta. You have some sting jet trajectories that reach lower than the dry intrusion. Same with the winds. You can see that actually the strongest winds are associated with the sting jet rather than the dry intrusion on the cold conveyor belt. And you can see here something quite typical of a sting jet. As it descends, it dries up, and you can see that signal in the relative humidity. So having all these trajectories, I can also look at details of where they're positioned. So this is in a map, like horizontal cross-section or vertical cross-section, maybe not as much as try to do it like this. I'm going to do other ones, just to show you an example. And you can see that, as I mentioned, actually it's a sting jet that comes closer to the surface here than the dry intrusion, and that you have potentially different pockets of sting jets and dry intrusion. It's not just one sting jet and dry intrusion. So this kind of details you don't have at 1.6 kilometers. And so what really matters in terms of wind damage is where the highest winds are, where it's going to impact. So this kind of detail would be interesting. So the goal here was just to try to characterize these airstreams and to describe them in a manner that we haven't been able to yet. So I said we coupled them with waves, and what I've shown you there is just an atmospheric run. We have wave coupling going on as well. I didn't redo the trajectories yet with the wave coupling, but we have to first ask ourselves the question, what does wave coupling actually do? So wave coupling comes into the calculation of the drag coefficient. And as I said, the latest version of the bulk parameterization that we're using is the one developed in France by Marie-Noël Bouin that takes into account wave age. And so in an uncoupled mode, it does assume that it has a constant wave age of 0.5. You have to be careful here, we're talking about just the wind C partition. And so once we couple, what we do is we change this wave age to be higher or lower than 0.5. So we have either younger seas than we assume in the uncoupled version or older seas. And so I took a step back when the storm was over sea. And you can see here kind of the strong wind core. Here you have the front. And you can see that ahead of the front, we actually, once you couple, we have younger seas. And at the back, we have older seas than what we would have in the uncoupled mode. And so as you see here, there's a distributions of the drag coefficients in those two boxes, light blue uncoupled and purple coupled. And you can see that where the sea is actually younger, we have a big shift in the drag coefficients we put in. Whereas like back here, there's a smaller change, there's a shift, but a smaller change. And this is what is going to impact our winds. So these are kind of the things we would expect once we do the coupling. In the younger seas, we actually going to reduce the winds. We increase the drag, and we reduce the winds. So I haven't gone further on that because, as I said, running back trajectories at this kind of resolution is a huge computational effort, so it's still ongoing. So I'll move on to the last case study, which is quite particular, which is I started with some master student interns. They wanted to look at air-sea interaction, and there was this case that was being discussed and drew quite a lot of attention in recent years, which is a case of the storm Janos, which was called a Medicane for Mediterranean hurricane. And it has a structure that resembles a hurricane with what is an eye. And there are several of these storms that happen over the Mediterranean, about 1 or 2 a year. And as soon as the press sees something like that, they say it's a Medicane. Now, a Medicane is something that's still not very well defined, and there's a huge community that's trying to figure out, okay, how much does it resemble an actual tropical cyclones or more of an extratropical system. So this was a case study we started looking at. So Mediterraneanos formed offshore of Libya, went to the Ionian Sea, and then hit Greece. So we're going to look at this part of its development. And here, since it's something that's supposed to be like a hurricane, I told them that we need to add ocean coupling, so the full coupling. And so for the ocean, we have CROCO. And in CROCO, there has been some recent development where the wave impact has been better taken into account. So we have the latest version of the full coupled framework in France, of the French community, I guess. And so we did 4 runs: an atmosphere only run, an atmosphere ocean, an atmosphere ocean and wave, and then we added sea spray because sea spray was my previous postdoc, and I figured why not? We're getting maybe at speed, so it could be interesting. What you have here is the track. The black lines are analysis, the European Center IFS analysis, ERA 5 track in the dotted line, and then our tracks in the colors. And here are the minimum sea level pressure. And you can see that in the reanalysis, which are low resolution for us, not for climate scientists, you don't have a system that a very strong system. Whereas in ours, if you have the atmosphere only, you have the strongest system, and then once you add the ocean, this the intensity decreases. And here's the only measurement we have: the pressure, which is this station in Paliki. Sorry. And so why do we have a weakening of the storm as soon as we add the ocean? That's because the storm actually produced a cold wave, similar to tropical cyclone. So here you have satellite observation before and after the storm passes. So it's a 3-day, I did a difference between the 16th and the 19th. You can see here 2 nice cold waves, and this is what our model gives us, which cold wave temperatures going down to -4 degrees. And you also have a signal in the salinity, a strong signal in the salinity. You can see here a freshening mostly in the second cold wave and a shortening in the first cold wave. And I overlay here the rain patterns you have. You can see like the rain here like mostly falls in the second cold wave, and it's more to the left of the first cold wave. Oops, that's not a good. Sorry. Sure, anyway. Yeah. And we were quite lucky with this case study also that we have a lot of Argo floats that were around the track, and I'm just showing you just a quick example of something that we started looking into. That this is the model response. So before and after the storm, we have in temperature over 4-degree cooling and a substantial freshening. There's another profile here that's missing. Interesting. You see a similar cooling in the temperature from this Argo profile that was right around the storm. However, there's a huge bias in our salinity, so we need to still look into that. So coupling not only like changes the intensity because of the cold wave, but it also completely changes the 3D wind structure. So here you have just a map of 4 runs, and this is the ASCAT data that we have for this system. And you can see that once you add wave, your system becomes more and more symmetric, and even more so once you add sea spray. And these are just cross-section. So you have the left side of the storm and the right side of the storm, and you can see that you completely destroy structures on the right side. So it not only affects the surface, but the whole system. So I was interested in seeing if sea spray has an actual effect on the intensity. Here I'm showing you the intensity in terms of the 10-meter winds averaged in 1 degree around the storm. And you can see, so you have a decrease in intensity once you add the ocean, and even so once you add once you add the waves, and a tiny bit more once you add the sea spray. And this is due to the fact that once you add the wave, you do change the drag coefficient. Here it's with wave, here it's without waves, but you barely change it once you have sea spray. So what actually does sea spray do in this system? Well, it weakens the system because it changes the thermodynamics. So here I'll show you the cross-section of the system, that's in the atmosphere, of the potential equivalent temperature. you can see that it has a warm core, such as you'd see in tropical cyclones as well. And if I compute, so theta E here, it's a time series averaged in this box around following the storm. You can see that once you have sea spray, you actually cool the system. And when you cool the system, you also diminish the potential vorticity, so it's in this intensity. So sea spray and those kind of wind conditions for this storm actually has a weakening impact and not increased impact. All right, so this is kind of to give you an idea of what the work we've been doing recently and where we're heading with that. Also, speaking of medicanes, I've been very interested in getting some measurements in those storms. The issue is that they happen once or twice a year and that we don't really have the supersite or anything in the region. So a dedicated campaign might be difficult to have. There's something that the Greeks developed for the wind industry, which is a float mask. It'd be cool if you could put instruments on that, because that's likely in the good region. Or to try to have a longer term series of measurements out there. We are also looking at SAR images. So there's the ESA program on medicanes that's trying to classify historical storms to see if they're more tropical-like, less tropical-like. We're doing the modeling part of that. In terms of SAR images, as I told you before, interpreting the roughness in those images is quite hard. We see, so this is again storm Alex when it's over the channel. We see some roll structure in our model. This is our model, and this is the corresponding SAR image. And so we're trying to find the links between the two, between what we see in our model and what we have in the SAR. Because the SAR just gives you what the surface sees, but it has no idea of, like, it doesn't give you any information of what's happening in the atmospheric column or even in the ocean, which both of them impact, obviously, the roughness. We also have a big campaign planned for measuring, for sampling storms in the Atlantic. So it's the French part is purely airplane-based, with a plane that's going to fly out of Ireland, and some wind radars on the coast of Brittany. For now, there's no ocean measurements planned. The closest to that will be a little Cessna that's going to be flying out of Brittany at lower altitude and will take some turbulence wind measurements. So this is a campaign that we're setting up. We got the funding for it. We are trying to figure out where to put the land radars. The Germans are joining with their huge instrumentation set up on land, and then we have the airplanes flying. It's part of a bigger international project, Nordic, where some Americans are also involved with the atmospheric rivers and so on. And the last area that we are trying to see to expand in terms of measurements is the Indian Ocean. So France has a lot of islands around Madagascar and further south, and we have an oceanography ship that does the rotation between those islands regularly, which also takes on instrumentation for dedicated field campaigns, but it always goes, it regularly tours those islands. And so PI in the lab has set up 19 instruments to measure all sorts of atmospheric variables, including also aerosols in that region, so continuously. And we recently deployed some sea spray measurements on that when it was doing its classical tour. The issue with doing it on their classical tour, well, the great thing is that it's a tag-along opportunity. The ship was going out anyway. The issue is that usually when the ships go out in that way, they avoid storms, they don't face into the storm, so we have very few hours of usable data. But that's something we could easily repeat, and with buoy deployment to have in a dedicated cruise. Another recent cruise aboard of this ship was the Windstorms. I'm going to try to look at where they took surface ocean and atmospheric plastic concentrations. And here we have a project that looks at scaling these, to estimate the plastic ejection from the ocean by scaling it to the sea spray aerosol source function. And why we're interested in that is because the ocean is actually thought to be a major source of plastics back into the atmosphere. It's been shown that there's more going into the ocean than what we actually measure in the ocean. and also back trajectories from remote sources have pointed out that the concentrations were coming from the marine, oceanic sources. And so this is the bubble class project, where we're gonna start looking at how, we'll try to estimate the water to atmosphere production of microplastics and nanoplastics. So this is with my collaborators at LOPS. There's a person who developed the microplastic ocean model within the PSCAS. I don't know if it's a biochemistry model that was adapted to also have microplastic. And there's actually an opening for a postdoc that would want to look at nanoplastics in that sense. And I'm interested in seeing how, once we add waves and wave breaking, how we change those estimates, so improve the estimates of the plastic ejection. And I think this is my last thing. I mentioned that mostly we look at extratropical cyclones, but I have one student from La Réunion. So La Réunion is the bigger island close to Madagascar, which is regularly hit by cyclones, and she is interested in looking at tropical cyclones. So with her, we're putting in the sea spray into the microphysics schemes of our model, and we're going to look at how that impacts modeling of two storms that we picked, for which we have some drops on data from this campaign, and we have good SAR images. So, right, so that was just to give you an overview of everything we're doing in the group and going to do. So basically, we're trying to understand what is responsible for those surface winds and try to look into different processes that are linked to ocean and wave interactions. And we do so mostly through modeling, but also through some field campaigns. And we're starting to collaborate with people that have looked at SARs in details. And I have not mentioned it yet, but that's something I really want to start looking into, is also rainfall. And so that's basically it. If you have any questions, I'm also here to look for potential collaborations, because I'm really interested in spending more time here in the future. So yeah, thank you very much.
Thank you so much, Sophia. Are there any questions from the audience in the room? Samantha, go ahead.
Can you repeat your conclusion on the asymmetries with the sea spray?
Sure.
I just want to make sure I'm following that.
Yeah. There is very wave and hand wavy. Because we haven't, so we are in the process of trying to have a way of quantifying asymmetry. Like right now, you can just see that you feel like the strong wind. So if you look at just atmosphere, you have a pretty symmetric vortex. And here you're starting to have asymmetry once you're at waves, because your wave field is asymmetric, which is accentuated once you're at sea spray, because sea spray is produced where you have to, this is dependent on the wave height. So it's going to accentuate the wave asymmetry. It also depends how you're going to input sea spray, and that can play a role of where you're going to.
Does the land have anything to do with it?
So it could, because breaking could be dependent on land. It depends again on if your source function is going to be depending on breaking terms of your wave model, of the significant wave height. Yes, it might impact it right there, but I don't think that far it does. But it's something to consider.
I think that's all deep water there.
Right, yeah.
Right, any other questions from the room? Susan?
In your part 2, you show results where you have the trajectories and you couple those to a wave model using wave age of the previous, or the slide 20.
Slide 20 here. Yeah. So I don't have trajectories in it, but yes.
How did you find the wave age that you're using?
Oh, it's the wave age that the wave model gives you. So it's a specific wave age, because wave age is a peak phase speed. This we're using only the wind speed partition, because the bulk algorithm we are using is developed as a function of the wave age of the wind speed partition. So with the wave model, we have wave spectra, we can partition them and have the phase speed of that partition.
What is the resolution that goes into your model?
Into which model?
This one.
Right, so here I'm showing you the atmosphere is at 400, but at 200 it's the same story, even at like 1 kilometer is basically the same story. Your wave model is discretized in frequency and in direction. It has the same horizontal resolution, but what's probably more important is that discretization and everything we use 48 direction and classic 30 frequencies.
400 meters for a wave model is very high.
Yes.
Like, do you even see any
No.
benefits at that? Yeah.
Probably not, and we stopped at 400 meters because we couldn't actually do it. It only benefits once you get coastal, and then you probably want an unrated grid.
Yeah. Is there no country in Europe flies reconnaissance aircraft operationally to storms?
No.
Is
We
there
don't.
any discussion about increasing need?
So, the big issue of the Mediterranean, for instance, is that you have a hell of a lot of countries around it, and each country, even like there's no, apart from the European Center, there's no one that models this whole part as a couple model. Each country does their own ocean or part of the ocean. So there's been discussion, especially with the people that are doing studying the medicanes, of trying to get a uniform thing, but there's nothing like. Yeah. And France, for instance, doesn't even model that part, like their operational stuff. Like includes Corsica, but doesn't include all that.
All right. Any other question?
There's a question in Zoom here from HS Kim. Can you ask your question through the microphone?
Okay.
Maybe we can read the question.
Yeah, Ron, can you read?
Let's see. Again. Oh, he doesn't have a microphone. Yeah, that's not good. Then maybe you shouldn't ask the question.
Okay, but maybe I can read it.
So the question is, between latent and sensible heat flux, which flux does sea spray make more impact on? Second, do you use particle size for the sea spray model? If so, what are the range of the size? What happens to flux estimates when the large sea spray falls? Have you plotted CD curves as a function? Well, maybe this should be better discussed by email. But,
With and without
yeah,
sea
you can
spray.
try to.
Yeah, so,
to
okay. Which one of the two, sensible or latent heat? So I didn't look into those details, but it's going to depend on, again, the size distribution you're going to put in. And so the size distribution we have is the one that Benjamin Barr wrote. Like, he has a neat paper on that where there are all those questions that I answered. We basically took his size distribution and I inputted it into the bulk model of BAL, 2011, if you want to look into all of that. Or you can email me and we can continue the discussion.
Yeah, so that paper that Sophia mentioned is Benjamin Barr and Shui Chen, 2023, I believe,
Yeah.
Journal Atmospheric Sciences.
Right. And for the CD with or without, I think it's there somewhere. You don't see it, but those two curves, the yellow and the blue. The yellow is with, the blue is without. You see there's barely a difference. I mean, there's a difference here, but not much.
All right, let's all thank Sophia.